So till now we have seen how a rotating magnetic field is produced, right? And we have also seen the direction. What will be the direction of the rotating magnetic field depending on how we are placing the windings, right? Now we will discuss the speed. What is the speed of this rotating magnetic field? When we saw how the rotating magnetic field was produced, we took one set of windings. So that means we have one phase here, A and A dash, another phase here, B and B dash, and finally we have C and C dash, right? So this produced what? A magnetic field rotating in the clockwise direction, okay? So now this rotating magnetic field you can visualize as a north and a south pole that is continuously rotating. So which one will form the north and south pole here? So if you're taking at a particular instant of time, okay, so we got 1.5 hm angle 90 minus omega t, okay. So now this position that we have, it is either 0 degrees or 180 degrees. So if you take 0 degrees, so when will this phase be 0? When omega t is equal to 90 degrees, or you can say pi by 2 radians. So at t is equal to pi by 2, what will be the direction? This will be the direction of magnetic field. Now you can see here, this is external to the stator. So that means this will be the stator, and whatever magnetic field lines that you have, they will pass like this through the stator, okay. So now this part here, this part of the magnetic field line, this is internal, okay, and this is external. And now we know that for a magnet, the direction of magnetic field is from south to north in the internal magnetic line, and it is from north to south external to the magnet, okay. So here we have the at t is equal to pi by 2, the magnetic field direction is from this point to this point. So this is the external path, okay. So at external it is from north to south. So we have here north and south pole at this point of time. If you are taking at t is equal to 0, let us say, then what will be the phase of the magnetic field? It will be in this direction, okay. So then that means that the magnetic field south pole will be here and north pole will be here. What about at omega t is equal to 3 pi by 2 radians? So this is all omega t, not just t, omega t, okay. So when omega t is 3 pi by 2, then you're going to get the phase minus pi. So in that, at that instant of time, this will be the direction of magnetic field. So then what will happen? North pole will be here and south pole will be here, okay. So what is the polarity of the pole will depend on which time instant that we are taking, okay. So now we have established the rotating magnetic field, how to represent it in terms of a moving magnet, okay, which has the north and south pole. Now we can understand the speed very easily. You can take the different time instants. At t is equal to, at omega t is equal to 0, we have this as the south pole and this as the north pole. At omega t is equal to pi by 2, let us say. The south pole is here, north pole is here. And at omega t is equal to pi, let us say. In this case, this will become north pole and this will become south pole. At omega t is equal to 3 pi by 2, we have this as south pole and this as north pole. And finally, at omega t is equal to 2 pi radians, we have the same old original position, right? This is south and this will be north. From here it will move a quarter more cycle, so it will return to the original position. At omega t is equal to 0 also, south was at the top, north was at the bottom. At omega t is equal to 2 pi, we have south at the top and north at the bottom. So what is the time period of the rotation? That means how much time the magnetic poles are taking to complete one full mechanical rotation around the stator. It is 2 pi by omega, because from omega t is equal to 0 to omega t is equal to 2 pi, we are completing one full rotation. The magnet is completing one full rotation. So that means this is the time period. But this is also the time period for what? The three-phase electrical currents. So that means the frequency, whether it is in hertz or in radian per second, the mechanical frequency, that is how fast this magnet is rotating, this is equal to the frequency of the electrical current that we are giving. So you can write here frequency of the rotating magnetic field, that is around the stator surface, and this is the frequency of applied current. Okay, so this then becomes the mechanical frequency and this is the electrical frequency. So that is why we are using the subscript m and e here. So this is in hertz, right? Similarly, the angular frequency, that means omega m, which is in radian per second, this will also be equal to the electrical frequency. Okay, but remember, this is when we have two poles. Okay, now it is also possible to have more number of poles. So how is that? Instead of one set of three-phase windings, we are going to use two sets. So instead of 6 slots, you are going to have 12 slots. Okay, so we can first draw the slots here. There will be 2 slots. So that total number of slots we will have 12. Now how the windings should be placed so that we can get 2 poles, that we can take the help of the single set. That means in the previous case we took something like this, right? So what were the coils here? This is A dash, B dash, C and C dash. So we got here A, after A we have C dash, B, A dash, C, B dash and then back to A. This was the cycle. Now the same cycle we want it to repeat twice so that we get 2 magnetic poles. So then what will come here? A, C dash, B, A dash, C, B dash, A, and once again it repeats. C, B dash. Finally you can write A again. But now you can use the subscripts. This is A1, C1 dash, B1, A1 dash, C1, B1 dash. Now next time when A starts, we can use the second set of windings. A2, C2 dash, B2, A2 dash, C2, B2. And finally again the first set is repeating. So that's what we can write here. This is A1, C1 dash, B1, A1 dash, C1, B1 dash, A2, C2 dash, B2, A2 dash, C2 and B2 dash. So now you can see here that one coil, the one end of a coil is starting here, A1, and it is ending here. This is the other end of the coil, A1 dash. Okay, but in this way if you keep, then you're going to get the same pattern repeated twice so that you're going to have 2 magnetic poles. Here you had only 2 poles. Here you're going to have, let's say this is where the north pole is present, and opposite to this you will have another north pole in 180 degrees. Here you're going to have a south pole, here a south pole. Okay. Now the position of these poles, it will depend on the time instant. Alright. Now in one electrical time period, what is going to happen? One electrical time period in the sense the time period taken by the electrical current, the 3-phase electrical current. In that time instant, each pole will rotate only halfway through the stator surface. That means only 180 degrees. Okay. So that means when the electrical angle becomes 2 pi, the angular displacement, the mechanical angle, that means the angle that is covered by the poles along the stator surface, it is only pi radians. Okay. So that means what is happening here? Theta E is equal to 2 times theta m. So that is why the electrical frequency will also be 2 times the mechanical frequency. Okay. So this is what we got for 4 poles In 2 poles, what did we get? Fe is equal to Fm. This is for 2 poles. So that means we can write in a generalized manner. What we can write is for p number of poles. Okay, if p number of poles are present, then we can write Fe is equal to P by 2 Fm, where P is the number of poles. This is in hertz, and also we can write the same in radian per second, angular frequency. Omega E is equal to P by 2 omega m. Okay, so this is the generalized expression. Now we can get in terms of the revolution per minute as well. This is in radian per second, angular speed. This is in hertz, frequency. The frequency is the number of cycles in 1 second. So that means number of revolutions in 1 second. And the speed in revolution per minute, what is it? Number of revolutions in 60 seconds. Meaning that simply Nm is 60 times Fm. So this, if you substitute here, what are you going to get? The final expression Fe is equal to P by 120 into Nm. From here you are going to get the speed, the revolution, the speed in revolution per minute, 120 Fe by P. So this is one important formula which we will be using time and again. This is the speed of the rotating magnetic field. Okay, so make sure to remember this expression.